Good morning everyone. Welcome to PG Pathshala. I am Dr. Pankaj Tandon from Atomic Energy Regulatory Board, Mumbai. The subject on which we are talking today is biophysics, and the paper on the module is nothing but fundamentals of nuclear medicine imaging. What is nuclear medicine imaging? As you all know, in most of the hospital, the word nuclear medicine is being used. What is nuclear medicine imaging? We have to understand that first. There are three different kind of imaging procedures, or we can say nuclear medicine imaging, application of radioisotopes in nuclear medicine imaging, and second is in radiotherapy and diagnostic radiology. To understand the concept of nuclear medicine imaging is one of the objective of this particular presentation. In what way this is different from other imaging modalities? What is the role of radiopharmaceuticals which is being used in this imaging? What are the devices being used for diagnosis of the disease? How it enables students to develop an understanding of the physics principle underlying these imaging techniques and awareness of these clinical applications. So, these are the 5 different objectives which we are trying to cover in this particular topic, that is fundamentals of nuclear medicine imaging. When we talk about introduction of this particular topic, the first thing which comes about, what is nuclear medicine? Nuclear medicine is a branch of medical imaging that uses radiopharmaceuticals to examine the function of structure of organ and tissue. The main difference between the nuclear imaging and other radiological tests is that nuclear imaging assesses how organ functions, whereas other imaging methods assess anatomy. It means when we talk about X-rays or CT or MRI, what we get? We get anatomical structure of a human body. But if you would like to know that how the organs are functioning, this is the only technique available which is utilizing the radiopharmaceuticals to image and how it gives the functioning of that particular organs. A radiopharmaceutical is generally made of 2 parts that we'll see in the further slides. First is a pharmaceutical that targets a specific organ or tissue, and a radioactive material or called radionuclide that gives us small amounts of radiation. It means radiopharmaceutical is a combination of a pharmaceutical and a radionuclide. The pharmaceutical part acts like a chemicals that the body normally uses, so the body tissues take up the radiopharmaceutical. The radioactive part gives off the radiation, gamma rays, that is detected by a special device. It means the drug which is generally being used for treatment of the disease, here we are using for diagnostic and therapeutic purpose the radionuclide. But we don't use direct radionuclide, we have to tag with different compounds to make a radiopharmaceutical, and how this radiopharmaceutical is being used for the diagnosis and treatment in case of nuclear medicine. As we talk about a special device, what is a device? This device is nothing but a combination of detectors where the radiation which is coming out from the patient is being detected. The device used may be a gamma ray, or nowadays we use for molecular imaging techniques positive emission tomography, and earlier when we started we were using scanner or probe. It means this was way back in 1950s where rectangular scanners or probe were used, and then we came with the gamma camera, then we came for SPECT, then we come across positive emission tomography. So these are the devices which are being used to detect the radiation which is coming out from that particular human body. Newer devices available may be able to perform 2 imaging studies at the same time, such as SPECT-CT and PET-CT. What does it mean? It means it's a hybrid technology where the CT has been combined with the gamma camera or SPECT and PET, and this is called SPECT-CT and PET-CT. Nuclear medicine. as it defines the clinical application of unsealed radioisotopes or radiopharmaceutical. What is unsealed radioisotopes? Unsealed radioisotopes clearly define which are not sealed in nature. What does it mean? It is in a liquid or gaseous form. Then how these unsealed radioisotopes are used? These unsealed radioisotopes are tagged with a compound, and when you are tagging with a compound, it is called radiopharmaceuticals. It means nuclear medicine is a clinical diagnosis or the treatment of the disease by a radiopharmaceutical. This radiopharmaceuticals is to be administered in human body, and finally whatever radiation which is coming out is to be detected by a device which we call as a gamma camera or SPECT or PET, but nowadays we have a hybrid technology where two types of scan can be taken place like PET-CT and SPECT-CT. When we talk about electromagnetic spectrum, and we should know about this particular thing very well. This slide tells about spectrum. It is from radio waves to gamma. When we talk about this particular thing, we see that there is a change in the wavelength, and the wavelength decreases, frequency increases. So, the radiation which is having high wavelength is having less frequency, which has less wavelength is a high frequency. How we can forget this gentleman whose name is Ernst Lawrence. In 1931, this gentleman, Ernst Lawrence, invented the cyclotron, and it becomes possible to produce artificial radioisotopes, because man-made radioisotopes are the only isotope which we can use, because otherwise the radioisotope which are naturally occurring, long half-life, are not useful for a clinical application. The workhorse which is being used, first and foremost thing is technetium, which was even produced by the smallest cyclotron in 1938 and by this gentleman. The first nuclear medicine scan had been taken by iodine 131 for thyroid purpose, which was carried out in 1948, point by point. It means there are many ways in which these radioisotopes are produced, and this gentleman has able to give us technetium and iodine by this particular technique. Now, how we can forget this particular person whose name is Anger, H-A-L Anger, and based on this particular and because of his name only, the first camera which has been designed was named as Anger camera in 1957. 1967, SPECT, single photon emission tomography with Anger camera. What it does, you rotate the camera on a chair where a patient is sitting, and you can able to take the scan. In 1978, first commercial gamma camera based on SPECT system was invented. It means we started the work in 1951, and 1978 we could able to make in first SPECT gamma camera. The beginning of PET, the technique of counting gamma camera from positron annihilation, had come about in 1951 and images were produced in 1953. It means we started our work with a probe or actinium scanner, and now we are in the era of PET, positron emission tomography. Not even a single PET, but we have many PETs in our country which are coupled with CT called PET-CT, which can able to take the anatomy and we can say physiology of the patient, and finally when we fuse both the things we can able to find a good quality image. Now again we discuss about what is nuclear medicine. Nuclear medicine is very unique because it helps doctor view how your body is functioning. As we defined our previous slides, the other imaging techniques are there like X-rays, CT, MRI. Then why the nuclear medicine is there? We are emphasizing it because it tells about the functioning of the organs, functioning of the body. This type of imaging takes very small amount of radiopharmaceutical and follows their path and progress through your body. It means this radiopharmaceutical acting like a tracer. When you inject or administer, what it does? It goes to the body, it mixes with the blood, and finally the pharmaceutical takes that radioactive material to the place of choice where you are going to diagnose that particular organ. X-rays or CT scan can show how something in your body looks, but nuclear medicine can show how your body actually works. It means it is playing a very, very important role. I can give an example to you. You have a dead dog or live dog. When you take a scan by using X-rays, you can be able to find out whether the dog is dead or alive. But if the similar examination has been taken place by nuclear medicine, you can able to find out, yeah, this dog is dead or alive because it gives the functioning of the body. Nuclear medicine is a type of molecular imaging. Why we use the term molecular nowadays? Because we are using the radioisotope like positron emission, which gives and which annihilates and gives 2 photons. It means you can able to diagnose the disease at a cellular level. That's called molecular imaging techniques, often called by using radiopharmaceutical to evaluate the body function and process. This type of imaging can be used on all types of living things, but we are concerned with using this technology to help diagnose and treat human beings. It means nuclear medicine is not only for the diagnosis purpose, but it is well being used for treatment purposes also. It means what we are saying is, what we are emphasizing is that nuclear medicine is the only modality available in our country which can be used for imaging as for therapy purpose. X-rays, CT scans, MRI gives good anatomical picture to you. They can able to say, yeah, structure to you. They can by this we can able to diagnose the disease. But apart from that, for getting the function of the body, function of the organs, nuclear medicine plays a very, very important role. It can be used for therapy purpose also. It can actually be used to treat the body. If you are undergoing a therapy process, then large amount of radiation will be used to treat cancer or thyroid disease. If you recall, iodine-131 is the isotope of choice for treating thyroid cancer. But today, we are able to treat the liver by using new radiopharmaceuticals. It means there are different kind of radiopharmaceuticals are available today for different diagnosis and therapy purpose. Why is nuclear medicine so important? I think by this time you understand why I am emphasizing more on nuclear medicine. Nuclear medicine imaging can help with early detection or discovery of changes in your body's function. It means you can able to diagnose the disease at early stage. When you can able to diagnose this at cellular level, it means you can able to treat early and the patient can be cured. Physician needs to accurate diagnosis first, so they can formulate an ideal treatment plan specifically for your needs. Until unless physician knows about it, how your organs are functioning, then it's not possible for them to make or formulate a treatment plan. This detection could help your care team avoid having to perform invasive procedure and possibly treat the problem without surgery. It means you can able to non-invasively you can able to treat the patient without doing any surgery. What will they do to me during a nuclear medicine procedure? This is the important question which comes in the mind of a patient. He would like to know, he wants to understand what is going to happen whenever the nuclear medicine procedure is being performed on that. You will be given an imaging agent, as we are talking about radiopharmaceutical, which will not give any harm to you. This could be given to you in a variety of ways, possibly by swallowing a pill, through an injection or inhaler, or even a special meal you will need to eat. The imaging agent will travel to the specific organ or tissue that needs to be studied. You will have pictures of a body taken with a specialized camera or specialized device which we are talking about, like a gamma camera or SPECT and PAT, and your medical team will receive the images of body to review and evaluate. It was very simple. When we take any kind of drug, here we don't call drug, we call radiopharmaceutical. Different mechanism it goes into the body. Radiations are being emitted from the organ which we want to diagnose, and after detection by these special devices, images are being created, and these images are being utilized by the doctors to able to design or formulate the treatment regime. Most radiopharmaceuticals used in nuclear medicine procedures can be detected externally using special detectors. I'm keep on emphasizing those important things. One is radiopharmaceutical and other is devices. If the device is good, radiopharmaceutical is good, you can able to diagnose the disease at a very early stages. Cameras works in conjunction with computers to form images that provide data and information about the organ or area of body being imaged, and finally based on this only doctors can able to make a regime to treat the disease. The radiation dose received from a diagnostic nuclear medicine procedure is compared to that received from some diagnostic X-ray examination. We know these radiations are being used. Definitely these radiations are being used to diagnose the disease. It means when this radiation is there, thinking comes that it is going to give some kind of dose. These doses are very minimal. The dose received in case of nuclear medicine is similar when we are taking any kind of diagnostic X-ray examination. But you see the benefit. You are able to diagnose at a much early stage. And once you are able to diagnose, doctors can able to treat you and you are going to be cured in much very simpler non-invasive way. Now we talk about the principle of uptake. Two components, radiopharmaceutical again, why, and each and every slide I am talking about this, a radionuclide and pharmaceuticals. It is not a drug, but it is a radiopharmaceutical. In designing a radiopharmaceutical, a pharmaceutical is first chosen on the basis of its preferential uptake. Let us suppose we want to treat or want to diagnose a lung, or want to diagnose a thyroid, or diagnose a kidney. Definitely pharmaceuticals are going to be changed, but radionuclide remains same. Maybe technetium-99m, which is the workhorse for conventional nuclear medicine. And when we talk about PET CTs, the workhorse is fluorine-18. It means these two radioisotopes are very important. So what I am again saying is, first you have to take care of pharmaceutical, which is going to be used for localization purpose, and then finally the morphology, and find this, and you can able to physiologically of the organ can be assessed. This radiopharmaceutical is nothing but it is designing of a radiopharmaceutical. A pharmaceutical is first chosen on the basis of its preferential uptake localization by a given organ, or its participation in the physiological function of the organ, that is morphology, and or the physiology of the organ can be assessed. As I am keep on emphasizing, the important workhorse in conventional nuclear medicine is technetium-99m. How it is being produced, that we are going to discuss further. And iodine-131, which is being used for treatment of thyroid disease in early stages. These are two important things. Whenever people talk about diagnostic procedures, the important radioisotope which comes to our mind is technetium-99m. And we talk about thyroid, iodine-131 is the isotope which comes to our mind. Now we have understood radiopharmaceutical. Again, radiopharmaceutical gone inside the body, radiation start coming out, and finally what happens? It is going to be detected by special device. This special device is nothing but gamma camera. What is gamma camera? Gamma camera is an image acquisition mode. It is having some collimators. It is having photomultiplier tubes. The radiation which is coming out from the patient, it interacts with the collimator. What collimator does? Collimator is going to align the only radiation which is coming out in the parallel directions. Then it interacts with the photomultiplier. What photomultiplier does? These photons comes, hit the photomultiplier tube, and finally electrons are being emitted. These electrons finally going to give the signals to you, and you can get an image. Then, as in the earlier slide we are talking about collimators, they are made of lead, which are basically material to absorb the radiation which is coming out from different angles. Then photomultiplier tubes, PMTs, and then we have a nuclear medicine tracer which is being administered. This administered radiation dose is giving some kind of radiation which is being passed from the collimator. It hits the PM tube. PM tubes, the gamma rays which is being emitted by the radio detected outside the body is by gamma camera, and this gamma ray impinging on the sodium iodide crystal which is dense enough, this converts light which is detected by the photomultiplier tube. What exactly is happening? It means the radiation which is coming out from the patient, it passes through the collimator, hits or targets the sodium iodide crystal, which is a detector. What the detector does, whatever radiation is coming, it hits and finally it gives gamma rays. Gamma rays is going to convert it, it hits the photomultiplier tubes and you get a signal. From this signal an image is being created. This particular picture or slide or photo will give more clarity to you. The photon is conveyed by a scintillation crystal to the flash of light. This crystal is nothing but sodium iodide thallium activated crystal. Thallium is a dope material and sodium iodide is a detector. Then this photon which is coming, it hits and the light is generated. This light finally hits the photomultiplier tube, which is converting this light signals to electrons, which gets multiplied by different diodes which are coupled with different voltages, and with a lot of electrons being generated, and the electrons is finally going to give a picture and image is being created, and the object in this our case is a patient. So, as we were talking about, the first important device which came and by which we can able to diagnose this radionuclides are a retinal scanner, or we can say this is having contains a probe. So, what it does is whenever any signal is coming, when it comes and it hits the PM tube, signal is generating and this probe what it hits that particular page, and in this way this particular probe is moving all around the patient, and as and when it is able to detect the photons, it is going to give a hit on that particular page or a device, and in this way you can able to diagnose, okay, this is a region where number of photons which are coming is much more, so there may be certain problems in that area. So, this was the earlier you can say device which is being utilized, and but because of the change in the technology, now we are talking about today's as PET and SPECT. So, the reason is that during those days when this particular device is being used, and we used to get this kind of images which is in a dot matrix kind of image, doctors may not be able to find out, okay, that particular disease is located at which region and because at which depth, because our all organs are in 3-dimensional in shape. So, but it can able to find out, okay, there is certain you can say disease or certain location in the body which is not behaving properly, there is some kind of abnormalities. So, in this way earlier days this was the devices being used. Then there is advancement taken place, and a device which has come across is a gamma camera. The gamma camera used to show how the radio pharma distributes itself through the body or is taken up by the specifically targeted organ. It means either we talk about retinal scanner or talks about gamma camera, which is a modality you can say upgraded or updated version. But here you do not get a kind of dots, but you get a image like you get an image like an X-ray image. The detectors is going to give the 2-dimensional image of the organ which is emitting this kind of radiation, which is called gamma camera. But again the problem in this gamma camera is you can get image of 2-dimensional and you can don't able to find out the depth of the disease, which place that disease is going to be there, because it only tells about the hot region and cold region, and on the basis the doctor has to presume, okay, this may be the location where the disease may be there, and then how he has to really define the treatment modality or treatment regime. Then again advancement taken place, and the devices which has come is single photon emission computed tomography. Before that also this particular camera which we are talking about, gamma camera, is going to be used at 4 different angles and able to get the image, and they have to reconstruct the image to make it 3-dimensional, but again you are not getting a good quality image which will help the doctors to decide the location of the disease. Then this particular SPECT came which rotates around the body, and you can get an image of the organ in 3-dimensional way. As the term itself defined, a single photon emission computed tomography. How we talk single photon means the technetium-99 which is being used is going to emit only one type of photons of monogenetic photons of 140 keV. So it is called single photon because 99.9% the emission is 140 keV. But when it is being emitted and the camera which is going to be rotated all around the patient is going to create different kind of tomograms, different slices, as you can take an apple and then cuts into different slices. So you can able to cut the organ in different slices when the camera rotates all around the body and captures the photon which is being emitted by that particular organ. Then it means the SPECT camera looks at a patient from many different angles and it is able to demonstrate very precise detail within the patient. Information is presented as a series of planes that corresponds to certain depths within the body. The plane presented may be a series of coronal, sagittal, transfer, oblique slices. It means the planes which is being formed because of movement of the camera gives a coronal image, sagittal images, transfer images, and then we have to use different kind of algorithms to convert these images into a three-dimensional image because you have to make some kind of mathematics you have to use. Then we come across the PET images, or we call about the PET scanner. The PET scanner is nothing but again the new era technology where we are going to use the radioisotopes for molecular purposes, and you can able to devise not on the organ base, you can able to take to get to know about the cellular level, the disease, or you can find abnormalities. So it is called positron emission tomography, as I mentioned earlier that the workhorse in case of conventional nuclear medicine is a technetium-99, but in case of PET it is you can say fluorine-18, and fluorine-18 is basically is positron emitter, and positron when it emits it annihilates with electron to give two photons in two different directions and 511 keV, and this photon is going to give the quality images to you. So what we can say that PET is used to study physiological and biochemical function within the body. Process studied include blood flow, oxygen, glucose and fatty acid metabolism, amino acids, transport, pH and neuroreceptor densities. As on-site electron is required to produce a very short half-life PET radiopharmaceutical, because one thing very important is there when we talk about technetium-99m, it gives it gives a monoenergetic, no doubt, but 140 keV, but the half-life is 6 hours. But here important thing is, though it is the radionuclides which is going to be used are very short half-life. Like fluorine-18 which we are talking about is giving 110 minutes, so you can able to transport from one end to other end. But the same thing or same situation may not be good in case of carbon 11 or nitrogen 13 and oxygen 15, which is further in few minutes, like in 2 minutes or 10 minutes or 20 minutes. So when we talk about minutes and we want to transport the radionuclide from one end to other end, it may be very difficult. And because these radionuclides which are being used in case of PET scanners are being produced from cyclotron, so definitely we need to have a cyclotron at our place, short half-lives. But more 90% examination you can do with fluorine-18. But suppose some time of clinical examinations which are very typical in nature may require other kind of radionuclides which are produced from cyclotron, which are short half-life. This particular image, if you see, you can able to appreciate that how the normal distribution of the bones can take place and how the abnormal takes place. You can see the different kind of hotspots are coming off. In this way, you can able to find out. Of the same picture, you can take with the help of you can see MRI or CT. You may not be able to find out the functionings of different. You can able to see the structure, but you cannot able to find out the disease location where this particular nuclear medicine helps. Now comes about how these radionuclides are produced. When we talk about technetium-99m, technetium-99m we all know is going to use from a generator. There are three different forms major forms we can say by which this radioisotope production take place. One is reactors, and second is accelerators, and third is generators. We are focusing more on generator on this particular presentation because the technician we are talking about, which is the workforce or workhorse you can say, in case of conventional nuclear medicine. These generators are basically constructed on the principle of decay growth relationship between a long-lived parent and its short-lived daughter radionuclides. What does it mean that long-lived parent and the short-lived daughter means? That the parent which is going to decay is going to give a daughter radioisotope which is half-life is short. Here we are taking molybdenum-99 as a parent radionuclide which is long-lived. It is 67 hours usually. So when this molybdenum decays, it is going to give technetium-99M. And this particular thing is available in the form of a generator. So it means it is a kind of milking process. It means the parent is decaying and finally daughter is coming. So the half-life is 67 hours, decaying to technetium-99, which is half-life is 6 hours. The important generator lies in the fact that they are easily transportable. It is a very small form you can say, and you can transport from one place to other place, and it can serve as sources of short-lived radionuclides in institutions located in remote areas where contracting the service of radiopharmacy is impractical. What does it mean? We don't want to transport the radiopharmaceutical itself, but we are giving the radioactive nuclide generator in that particular hospital, where the purpose is to eluate the technetium which is being produced from molybdenum, and finally you have to tag with different kind of compound to make a radiopharmaceutical, and then use this radiopharmaceutical to diagnose the disease or treatment purposes. So this is the one form of you can say production method in which the technetium is produced, and very important way, and very what you can say, it's being used in most of the places, most of nuclear medicine department in our country. The importance of radionuclide generator lies in the fact that they are easily transportable and serve as a source of short-lived radionuclide in institutions far from the site of any cyclotron reactor facility. As we have seen that the generators are there. This is not the only generator we are talking about, molybdenum, technetium. There are other different generators like germanium, gallium, strontium, yttrium that we are going to talk about in few other slides. So what we can do, instead of transporting the radionuclide which is being produced from cyclotron, no doubt cyclotron are used, the reactors are used for making other forms of radionuclide which are being used in medical applications, or you can talk about in research and agriculture, industrial purpose. But generator is also one of the most important thing which is now being used in many of the hospital molybdenum technetium. Generators are either ion exchange resin or alumina column which contain parent radionuclide. I was talking about parent is molybdenum in this case, and it decays to give the technetium, and finally our job is to elute technetium from there. With time the parent radionuclide decays to a daughter radionuclide that is not absorbed in the column. We are talking about in further few slides that the parent is in the alumina column, and the parent is decaying, and the technetium which is being generated is not going to absorb, is going to remain free, and that's what we can able to elute by putting a saline in the pertechnetate form. Again, we summarize when we talk about generator, it consists of a glass or plastic column fitted at the bottom with a fritted disc. I'll show the picture to you next slide. The column is filled with adsorbent materials such as cation or anion exchange resin, alumina or zirconia on which the parent nuclide is adsorbed. The daughter radionuclide grows as a result of decay of the parent, because parent, that is molybdenum, keep on decaying with 67 hours half-life, half of the you can say activity decays out and forms the technetium, and technetium remains there and is having a half-life 6 hours, it just started decaying. So our job is to take out somewhere this technetium which is available from this particular generator, and then you can able to, what you can say, combined or tagged with the compound which is going to be used for different kind of diagnosis of different kind of organs and make a radiopharmaceutical. Because there are difference in the chemical properties, daughter activity is eluted in a carrier-free state with an appropriate solvent, leaving the parent on the column. Definitely, the parent being used is molybdenum, and the technetium is different. You can say isotope itself. So it is mostly a carrier-free because, but some amount of molybdenum comes out, and that is why we have to do certain kind of quality test to see to it whether it can be administered in a human body or not. A radio generator must be sterile and pyrogen free. Why? Because finally the eluate which is coming out is a technetium, and that is very important because finally you are going to administer it in human body. So you cannot take a risk on that. So there are different kind of QA test is being performed on the technetium, you can say pertechnetate which is coming out, and then for it is to be labeled with a compound pharmaceutical to make a radiopharmaceutical, and again some kind of QA test is being done. The generator system may be sterilized either by autoclaving the entire column or preparing it from sterile material under aseptic conditions. Often bacteriostatic agents are added to the generator's column. Elution or milking of generator must be carried out under aseptic conditions. It means the first generator which is being used to give us technetium itself, we have to see to it it should be sterilized, and finally when the technetium comes out and you are going to tag with compound to make a radiopharmaceutical, we have to do the certain test QA test to see to it whether it is you can able to administer in human body or not. It means an ideal radionuclide generator should be simple, convenient and rapid to use and give a high yield of daughter nuclide repeatedly and reproducibly. It should be properly shielded to minimize the radiation exposure and sturdy and compact for shipping. Definitely when it is going from one place to other place, then we have to see to it it should be you can say sturdy, and already the column which is there in which alumina column which is molybdenum is absorbed, it is in the lead container, and finally you have to shield it in proper way so that you can able to transport to the place where the finally elution takes place. The generator eluate must be free from the parent radionuclide and absorbed material. There are important generators in nuclear medicine. As I was talking about, molybdenum technetium we are always saying, but there are tin indium generator, germanium gallium generator, and strontium yttrium generator. Very important generators are there. But again, when we talk about conventional nuclear medicine, which most of the examinations can be carried out is by technetium. Molybdenum technetium 99 is one of the very important generator. The molybdenum 99 radionuclide, again we say 67 decays to technetium, and technetium is a radioactive material which finally decays to a ground state to become technetium 99, which is having a half-life of 10⁵ years by isomeric transitions. So this is the generator which we are talking about. The generator, if you can see on the center side there is a column which is made of alumina, and finally in this column itself molybdenum is absorbed, any kind of parent radionuclide is absorbed, and there are two openings are there. From one side you have to put the saline. The technetium which is being formed during the decay of molybdenum is basically available with us, which is not being absorbed in the column, alumina column, and finally it comes out in the other vial in the form of pertechnetate, you can see, and it is being covered with you can say lead as a shielding material. So it means from one end in the generator you are putting 0.19% sodium chloride, which is a saline, and from other end you are basically taking out you can pertechnetate, and this is the pertechnetate which is going to be used for examinations. So there are different production methods we have discussed, and we are going to discuss in further presentations like cyclotron, nuclear reactor, and you can say radionuclide generator by activation process. And if you see the characteristics, the bombarding particle is different in case of cyclotron. The particle which is going to be accelerated is a proton, deuteron, or alpha charged particle we can talk about, which can be accelerated. In case of reactors, neutron is a bombarding material, a bombarding particle. In case of reactors, where is going to be used neutron activation technique, where the target is to be activated by using neutron. And the radionuclide generator, where the production is by decay of parent to parent. The product, if you see in cyclotron, is neutron poor. In case of nuclear reactor, is neutron access is there. In activation, again, because you are activating the target with neutron. So, and again, in case generator is neutron, because neutron is not at all there. The typical decay process, if you see, is positron emission. Those which are produced from cyclotron are the positron emitters, which is coming out from reactors is a beta minus or electron, we can say. In case of nuclear beta particle, whether it is talk a reactor or talk about activation, in both ways beta decay takes place. But radionuclide generator, there are different kind of transition. Isomeric transition is there in case of molybdenum, and whether it is carrier free or not, again the very important thing, yeah, it's carrier free because cyclotron is bombardment taking place or target by proton or deuteron. In nuclear reactor also, sometime when the fission take place, it is carrier free, but in activation it is not carrier free. Some kind of carriers are produced while the activation taking place. In kind of generator, yeah, it is carrier free. When we talk about activity, whether it's high specific activity or not, cyclotron gives high specific activity, reactor gives a high specific activity in case of fission, but not in case of N-gamma reaction when the neutron activation takes place. And generator, yeah, it is a high specific activity. Cost, if you see, cyclotron is a very costly mode of thing, because it is being used in reactors, because reactors are there for research purposes. We are able to produce these different radionuclides. But these reactors are not only being commissioned for for production purposes. In case of fission, some radionuclides are being produced, which is being you can separated out for the medical purposes. Then if you talk about the cyclotron, there are thallium, iodine 123, gallium 67, fluorine, as we are talking about, O15, cobalt 57 produced. If you talk about reactors, which is a fission base, moly 99, which is a high specific activity. If your same moly, if you produce by N-gamma reaction from molybdenum 98, the specific activity is going to be low when a neutron activation takes place. And the radionuclide generator is a molytechnetium, germanium gallium, strontium, yttrium. The different generators are there. In summary, if you go about the radiopharmaceuticals are used in unsealed form in nuclear medicine for diagnosis and treatment of disease, and the equipment called gamma camera detects the photons emitted therewith. With the advancement of technology, there is a change in the modality, that is initially we were talking about actinic scanner or gamma probes, we are talking about gamma camera and PET-CT. With the advancement of technology, there is an advancement of production of many different type of radiopharmaceuticals for diagnosis and treatments. As the technology advancement is taking place, and when we have reached from gamma camera to the PET-CT, initially we used to talk about technetium label, but now for treatment purposes, various different new radiopharmaceuticals are available. Now, most of the radiopharmaceuticals are made available from indigenous manufacturers also. We can able to get this radiopharmaceuticals. We don't have to import this, because we have some plants available where we can able to generate this radiopharmaceutical indigenously. With this, thank you, and we can able to cover up most of the place, most of how this nuclear medicine imaging, what is radiopharmaceuticals, and what are different kind of methods of production of radionuclides. Thank you.